My name is Fang, and mass characterization and active optics mechanism testing. This is all base level testing, just like the DM. There's a list of the people academy who are each of the mechanism. There's the PAM academy, more FSM, Coronagraph, FCM, and also mass fabricated downloads. And also we have to make sure and recognize that the PAM mechanism is coming from Max Planck in Glasgow, Germany, and also the substrate from mask are coming from JAXA, Japan. This is a quick outline. Instead of going outline, we go direct pictures. So this is what we mechanism and mask we talk about here. Starting with there's a mechanism of fast error mirror, and also there is a focus control mirror, and there's a 6 PAM. Similar design, 2 group of travel for X horizontal range. And of course, on 4 of those PAMs have a mask also coming from the active optics delivered, which I'm to talk about. And so starting with mask, this was, as I said, some of the substrate for, especially for the shape pupil, the one with a lot of a black silicon one, and as well as the few silica for infocal PSF focal point mask. Those are coming from JAXA, and the mask was fabricated by the JPL's micro device lab, and they have done a great job. And then we were for this mask, what the characterization involved many measurement, and so we were measured basically using the high power microscope for the morphology informations and the dimensional. And also we use for some select mask, we use the atomic force scanning to see the fine structure of the PMGI for the focal point mask. Here's an example of high powered microscope. And based on for all the spots, we measure every single spot. We have a measurement. There's a color because the profile changes on a dielectric. And here is the picture of the atomic force microscope scanning of the profile. And combine those two, we can identify the mask property as well as mask quality. And for the measurement, we can see for the one spot we use, this one used for our HLC testing or chronograph doing the TVAC, and it was everything was hit on right on, and so that's the one of the beauty of that DL has been capable to do, and this will be hopefully in the future they can provide a similar technology and needed for our future missions. And we did not do all of AF measure for all the spots, even though we have 20 spare spots for HLC. Because the time consuming, also we worry about damage on the spot because those AF don't drag across the spot. And so, but again, we took a sample of this one, you can look at the direct images. You can see the profile, whether they match or not, because you can, those sort of give information in the imaging point of view. You can see if they are very close, similar, then we know they are good spots. So those are, all the spots has been measured and documented, and it was put in a model for both chronograph control and chronograph simulations. For the another sort of mask for the Leo stop and the field stop, those are made of thin, etched from thin silicon wafer, and those masks we mainly rely on this microscope images, high power scanning through the whole thing. Each mask we have the image like 500 megabytes of data for each of the individual things. So it's very detailed, high-powered images for both transmissive and focus on the edge, focus on backside, transmissive, and those are data we use for our modeling. And this is the example picture of this field stop. There are so many open hole slits and opening. Those are all individually measured dimensionally, as well as we identify any subtle defects. MDL has masks all beautifully made, but they are with the perfect made, we still have we try to find an imperfection using those sort of minor imperfection as an indication to ranking those masks to select our final flight mask and a flight candidate. This is the mask for shaped pupil, which is made of a black silicon on a substrate of silicon substrates. Those are we use the one substrate to make up 4 shaped pupil masks, and those masks has been measured by a high power microscope images, as well as the zygo measurement for surface flatness, and also we're using for the black to characterize the black silicon as well as reflectance. We have a dedicated test bed to measure the black side of the using the this is the taking with the images from the same witness sample with same fabrication run, so they have to represent the same process of MDL, and we measure their reflectance from dark side as well as from the bright coded side for the reflectance. So those are measured and make sure we have met requirement, and those are really all very made a very good measurement is a high power laser to make sure we can really see the darkness of the dark area of this shaped pupil mask. And this is a big picture of the measurement of zygo to make sure they are flat and their reflectance made a requirement. So those are in one of the few things we do for all of the mask we fabricated, and from those we rank those and working with system engineer make sure we select the best one for our flight. Then we switch gear to the mechanism. So we have a 6 mechanism for CGI to use to moving mask and optics, so we can change accommodate different modes. And for those mechanism are made of a contribution from the MPI in Germany, and they are in the same design with 2 different groups we call large and small. The difference is between the travel range between horizontal travel ranges for the 3 of the mechanism, which is have a large, slightly longer travel range, we call large, and then another 3 have small. Is all accommodated to our system design required for the motion and requirement clearance for the beam. And those are for the masks. For those mechanism testing, there are we group into 2 groups for verify their requirement. One for all mechanism, which is pure performance, not need required for a CGI electronics. The MPI did their testing using their GSE. So to verify all the requirement, which is summarized in this table, which is including all the repeatability, accuracy, run out, and so on and so forth. And one of the questions this morning asking about the how rigid this mechanism are. The requirement is 90 hertz, and we test them all at about 180 hertz during the first mode frequencies. And for those are the requirement we test at MPI. At JPL, we also test combined with our driving electronics. And those are different behavior. There's a verify their requirement required need combined with our driving electronics using our motion profile. And so those are testing done at JPL under different temperatures in our vacuum system. And we verify this performance at both the 18 degrees and to 50 degrees to 25 degrees C. Make sure they are required, meet the requirement. This is a summary, one of the example of the repeatability testing with our PAM-E, not just using MPI had did similar testing for the mechanism level, but this one we're testing with the electronics combined. This is some example of the repeatability, and as well as the this encoder noise. Those are all because related to the electronics and not what the electronics are. And we also doing the TVAC, we also did a lot of calibration to make sure our mapping for the index of the encoder, our mapping for the step motor counts, those combined together, we give an update for our driving need for operations under different conditions. And so those are being recorded periodically during our in-air testing as well as the testing. For Another mechanism is fast steering mirror. For those, we have a requirement for the tiptoe range, as well we're testing with the accuracy, jitter, all those things. So we're using a combination of different GSE. One, we have a back metrology system which is precise, but it's much slower, but they are price precise. So we're using that to capture, to verify some requirement, which do not need the speed. For the high speed dynamic properties, we're using the cost metrology system, which is up to 20 kilohertz sampling rate. And then, of course, then we have a requirement for surface flatness of FSM. We use the zygo to do that. So this is here example of the capture range, the tip tilt range, which is required tested on different temperatures, and as well to make sure we have this FSM has enough range meet the requirement. The requirement is 200 microradians. We test more about 100 to 250 each range. This plot shows an example testing of dynamics of this performance. Be sure we are FSM. We need power down, the jitter, and piston jitter, as well as the tip tilt jitter meet our requirement, and those are shows this results here. Those are just examples we have of testing of FSM. This is an example of FSM testing the surface figure error at different temperatures. Make sure that the mount is not being warped by the thermal. So those are the requirement shows they are very stable. The measured wavefront error is well within the requirement. For FCM, similarly, we have a driving requirement for the range, and FCM is made of two actuators, two stages. One is the core staging stage, which is using the step motor plus the lead screw. There's the 5 stages for the core stage is mainly for initial setup or system, which we not rely on to driving, doing a closed loop of focus control. Then there's another 5 stages which use the PZT, which is give a fine control. We can use that for our focus control loops. Here's an example of our testing for the 4th stage testing using the metrology system. We can measure the whole range of traveling with different steps, going back, and here's with the smaller steps, and we calibrate all their step sizes in 4 stages because of step motor plus lead screws. So they are the step ranges is a little bit scattering, and yeah, this is used for basically for our initial setup, and we probably just set it and forget it, never use again. This requirement is well, step size is less than 7 microns. This testing shows all things within 7 microns, and it's the mean step size to about 5 microns per steps. Here's an example for fine stages. This is driving by PZT with a it has string gauge, but it would not close loop locally. So the string gauge is operating open loop. Flight software will periodically checking the thing. And flight software will use that string gauge to control focus during the focus control. June was mentioned about that. So here's example for the testing of the fine stages with PZT for different scale now, talk about microns, and the total range requirement is 27 microns. We tested about a 40 micron-ish, so we have well enough margin for the total travel range. And then we have also testing for high-speed system to make sure that when the PZT was driving for the core stage moving will not generate too much jittering for both the piston as well as the tip tail. So those shows our requirement, requirement for this FCM devices. So that is pretty much a quick summary. What do we have there? We have a lot of mechanisms delivered. We tested in our system, and we make sure they are met requirement. All the masks has been carefully characterized and ranked and selected for our flight, and those data will be used for our modeling. And so everything is delivered and integrated and been tested in both FFT as well as TVAC. And so CGI has been successfully delivered. So that's our system. Thank you.